Section 5.6 is called Exponential Applications. And in exponential applications, you are going to be using this formula pretty exclusively. This is the exponential growth formula, and it's used for exponential growth, exponential decay, and continuous compounding. And occasionally these letters are going to change on you, but the form of the equation never will. This will always be your final amount. This will be your initial amount. The E is Euler's number. Rate is always going to be a decimal. So the rate will come into and go out of your equation as a decimal. And T is going to be your time, and the units are going to vary in these problems, so pay attention to the units. So the typical problem you will have will look like this. A painting sold for $207 in 1978 and it sold for $493 in 1989, assuming exponential growth, and then there's going to be a whole bunch of questions. First one is find the growth rate. So plug in the numbers you know. You know the final amount is 493. The initial amount is 207. We're trying to find the rate. And for some reason in these problems, they generally call it K. I'm going to stick with R. It shouldn't be too hard for you to switch back and forth. And the time, which is the amount of time between 1978 and 1989, or 11 years. And what we're going to do is solve this equation to find R. What we're going to end up doing is using the rules of logarithms to cancel that E, but we can't do it with that 207 out in front. So the first thing we're going to do is divide both sides by 207. And get that. Now I can take the natural log of both sides and remember, natural logs and e's are inverses, so they cancel each other out. So I get R times 11 equals the natural log of 493 over 207, or the rate equals the natural log of 493 over 207 divided by 11. And then I just have to punch that into my calculator. And get an approximate rate. And they're going to ask for different degrees of accuracy, so pay attention to how many decimals they want. Okay, next we're going to find the exponential growth function, and that's really simple. Once you have this, the exponential growth function is the initial amount, the E, the rate is a decimal, and the time. That's it. You're done with exponential growth function. That part was really simple. So let's walk through the other problems. The next one, what is the value of the painting in 2012? First thing we have to do is figure out how many years it is between 2012 and 1978. And that's fairly simple. We just subtract 1978 from 2012. We get 34 years. And we plug that 34 years into our formula. So we had our exponential growth formula. We plug our 34 years in. And just remember, when you're plugging this into your calculator, make sure you have parentheses around the entire exponent, or you will get the wrong answer. And when you plug that into your calculator, you should end up with $3,037.28. Now, doubling time just means the amount of time it takes 207 to go to 414. And we could set it up with 414 as the final amount and 207 as the initial amount, and then do our division. But whenever we have the words doubling time or half-life, it's easier just to put the doubling or the 1/2 out there, forget the initial amount, and then plug in the rest of the growth formula. And then solving for t will give us the doubling time. So we take the natural log of both sides, the natural log and the e cancel each other out, and I just switched sides here simply because I like my variables over on the left. It doesn't matter if you leave them on the right. And divide by the coefficient. So t is the natural log of 2 over 0.079, which is going to be approximately 8.8 years. Now let's try another one of the same type. When will the value reach 3,471? Well, for this one, I do need to put in the final amount over on the left-hand side. And again, I need to get rid of that 207 in front of the e, so I'll divide both sides by that. Now I'm taking the natural log of both sides, and natural logs and e's cancel each other out. And again, I'm switching sides simply because I like my variables off on the left, but it'll work if you leave them off on the right. Now I just divide by the coefficient. Plug that into my calculator and get about 35.7 years. Unfortunately, this is how long it will take to reach $3,471, and I want when. So I have to add that 35.7 years to 1978 to come up with the year when it will reach that amount. And you couldn't have a problem in this section without the infamous carbon-14 problem. Here we have carbon-14 with a half-life of 5,750 years, and some scientist has a fossil bone that has lost 52.5% of its carbon-14, and I want to know how old it is. Well, the first thing I do is I have to try and set up an equation with what I know. And just like the half-life, I'm not going to worry about the initial amount. What I know is if I lost 52.5%, I have 47.5% left, and written as a decimal, that's 0.475. So just subtract 0.525 from 1, get the amount that's left, and solve that equation. And the problem here is we can't. We have two variables that we need to find, r and t, and only one equation to do it with. So what we're going to do is go back to the half-life of 5,750 years and use that to define the rate. So for the half-life, I have no idea what the rate is, but I do know the time is 5,750. Take the natural log of both sides. They cancel. And I get a rate of the natural log of 1/2 divided by 5750, or negative 0.000121. And that's just this rounded to 6 figures. Now what I can do is plug this rate into this equation, and solve this equation. So take the natural log of both sides. They cancel out. Divide by the coefficient. And we get our answer of 6,152 years old.